think we can probably get started. People might still filter in, so just go slow through the introduction. Okay, so welcome everyone. Today we've got Jiayi Sun, who is currently a CITA National Fellow at McMaster. So Jiayi has just completed his PhD with Adam Leroy at the Ohio State University, for which he won various awards according to his CV. He's also working on many observational programs with ALMA, the VLA, and actually JWST as well. And he works on molecular gas and star formation in galaxies, which is going to be the subject of his talk today. So take it away, Jiayi. We're looking forward to it.
Thank you so much for the introduction, Ted. So it's my great pleasure to virtually visit you again at U of T. And I say again because last month in the CITA Jamboree, I think I just talked about my research on molecular clouds population in nearby galaxies here. And in that talk, my focus was on their environmental dependence and star formation efficiency. Today, I figured I probably want to talk about something different. So I'll touch on two related topics. The first part of my talk will be about dynamical balance, actually the balance between pressure and gravity in the molecular gas in nearby galaxies. And this topic makes it very straightforward to link molecular clouds to the entire galaxy ecosystem. And in the second part of my talk, I'll show you how to use observations of face-on galaxies to infer the gas distribution along the unobservable third dimension. So I would like to start my talk by describing two complementary views of how star formation works in galaxies. So the first view is best illustrated in this face-on cartoon of a galaxy. And in this galaxy, we have spiral arms, we have molecular clouds. Most of them are lying along the spiral arm, but some of them can exist in interarm regions. And these molecular clouds could hold a significant fraction of the total gas mass, especially in the inner part of the galaxy. Now we know that star forms in some of these clouds over time, but only a small fraction of the gas mass ends up converted to stars. And the remainder gets dispersed by feedback, and they possibly go to other gas phases, and this restarts the entire star formation cycle. So in this picture, we just view molecular clouds as individual star forming factories. And to get the total star formation rate of a galaxy, we just need to do a census of them. So we would sum over all the molecular clouds in this galaxy. For each cloud, we just measure their mass, which tells us the total gas supply. We measure a characteristic timescale for star formation, and typically people use the free fall time of the molecular cloud as a timescale indicator. And then there's this efficiency term that tells us how much of the gas mass are converted to stars over one characteristic timescale. So this is one way to think about how star formation process, how this process works in galaxies. And it seems like molecular clouds just do things on their own. And when we want to know the things about the entire galaxy, we need to sum over all. But there's another way to think about this process. And in that way, it no longer seems like molecular clouds can do whatever they want. And that picture is better illustrated in this edge-on view of a galaxy disk. So now I'm again showing you a bunch of molecular clouds. And to be more realistic, I'm also showing you a layer of diffuse gas in which the molecular clouds are embedded. Now, molecular clouds are dense, and again, some of them could collapse under self-gravity and form stars. But when stars are formed, feedback injects energy and momentum into the ISM. That creates turbulence, and these kind of turbulent motions actually help support the gas from collapsing and further form stars. And this entire cycle forms a negative feedback loop. And the way this works is that if you have a star formation rate, a temporal star formation rate that's higher than what it's supposed to be, you inject more energy and turbulence into the ISM that will create more turbulence and more support, and therefore your star formation rate drops down. So over time, the entire galaxy disk would tend to reach an equilibrium state. And in this equilibrium state, the hydrostatic weight of the ISM, which is given by the surface density of the ISM times this little g, the local gravitational field strength, this hydrostatic weight is balanced on average by the pressure near the midplane inside the ISM. And this pressure, because most of them are turbulence in origin, this is further maintained by feedback from star formation. And here I'm reading this feedback injection term as the product of the local star formation rate surface density times this this eta FB term. So this term stands for the feedback momentum yield. It is telling you the momentum injection per unit stellar mass formed, and it is typically expressed in terms of kilometer per second unit. Now, if we rearrange the term a little bit, we get another way to figure out what the star formation rate is supposed to be in the chunk of a galaxy disk. Now, you can see that it is determined jointly by the hydrostatic weight of the entire ISM and this feedback momentum yield. So I like this alternative picture of how star formation works, because in this case, molecular clouds are only part of the whole galaxy ecosystem, and their collective behavior reflect this galaxy-wide equilibrium state. So now the question becomes, does this picture actually work? And more specifically, we want to answer some key questions. First is, does the bulk ISM exist in that dynamical equilibrium? And because we know that the cold ISM are clumpy, a lot of the gas are clustered into molecular clouds, we also want to understand how do molecular clouds fit in that picture. And the second question we want to address is feedback actually capable of regulating star formation and maintaining them at the level that we observe in nearby galaxies? Now, to answer these questions, we probably need to know a lot about a galaxy. So if you just look at these terms, for sigma ISM, we need to know the distribution of the gas, including all the cold phases across the galaxy disk. And because especially the cold molecular phase is clumpy, we probably need to at least pin down this surface sensitive distribution down to individual molecular cloud scales. And then for this gravitational field, we probably need to know all the mass dominating phases in the galaxy, including the gas and the stars. This eta FB term is not easily directly observable, but we can observably measure this star formation rate surface density and try to back out this eta FB term. So that's how things will work in observations. And this requires a diverse set of observations tracing all the key components in the galaxy. So to do this, we select a sample of 28 galaxies from the FANGS sample. And this FANGS survey is a nearby galaxy survey that targets massive, mostly face-on and actively star-forming galaxies. And the bare bone of this FANGS project consists of CO2-to-1 observations by ALMA at very high resolution. So the resolution is typically 1 arcsecond, which corresponds to about 50 to 150 parsec in those galaxies. And this means that the CO2-to-1 observations we have across this entire galaxy disks allows us to know the gas distribution and kinematics on individual molecular cloud scales. And now, because FANGS targets a lot of nearby famous galaxy on the sky, these galaxies already have a rich set of ancillary data existing. So for example, we have H1 21 centimeter observations. A lot of these are come from old surveys like THINGS, Heracles, Viva, etc. But we also have data from a new FANGS VLA survey led by my previous colleague DS Utomo. And all these observations together trace the distribution of the volume feeding atomic gas in these galaxies. We also have near infrared imaging. Most of them are from the S4G survey from the Spitzer Space Telescope. We will also include some new data acquired by my colleague Miguel Carajeda. And these observations trace the distribution of stellar mass in these galaxies. And finally, we have archival GALAX, UV, and WISE near infrared data. And their combination tells us about the unobscured and obscured phase of the star formation rate in these galaxies. So now with this full set of observations, we have basically everything we need to go back and answer the questions. But there's a problem. The problem is that the CO observations we have from the FANGS ALMA survey has pretty high resolution on individual molecular cloud scales. But the other data sets, most of them have resolution of total KPC scale. So there's a gap in terms of the spatial scale probed by these observations. So we need to bridge this gap. And the way we do this is by calculating the cloud population statistics and then match them with the local post-galaxy environment. So more specifically, the way we do this is that we first divide each galaxy into KPC-sized chunks that are hexagonal in shape. So as you see in this plot, each hexagon here represents a KPC size chunk of a galaxy disk. Within each aperture of those, we first identify individual molecular clouds from our CO observation, and then we measure essential cloud properties such as surface density, turbulent pressure for each cloud, and then we do a mass-weighted average across all the clouds in that aperture. So this gives us a population average property across all the clouds in this region. And then for the other ancillary data sets, we do a similar thing, but we calculate the area-weighted average from the multiwavelength data I just talked about to characterize the host galaxy property in each aperture. So these observations tells us about the local area-weighted average atomic gas surface density, stellar mass surface density, and local star formation rate surface densities. So now combine all these terms, we are finally able to come back and address these two questions. Now for the first question, know that we cannot simply treat the entire ISM disk as a single smooth fluid, because I already mentioned that there are molecular clouds in them and they can hold a substantial amount of mass. So we need a model that actually works even in the dense molecular clouds. Luckily, we already have a large suite of these models from decades of literature on molecular cloud dynamics. The simplest version of such model is just isolated self-gravitating clouds. And in this picture, what we have are molecular clouds. Molecular clouds that are isolated from each other. They have internal pressure from turbulence, and that internal pressure is on average balancing their own weight due to self-gravity. But we know that molecular clouds do not live in a vacuum. They live in galaxy disks, and there are external gravity, mostly from stars. And sometimes those external gravity can be important. So this turbulent pressure inside the clouds should also balance out that extra external gravity. And finally, we know that molecular clouds are embedded in the volume-feeding atomic gas, which itself has pressure. So this atomic pressure actually sets a pressure floor. And the pressure in the molecular clouds should exceed this floor, and that excess matches the combined effect of self-gravity and external gravity. Now we have a model that seems to be working, and to be more concrete, we calculate the turbulent pressure inside molecular clouds based on the measured mass, size, and the velocity dispersion for each cloud. And then we measure this so-called dynamical equilibrium pressure, which is the expected pressure from the dynamical equilibrium hypothesis. So this includes all the three terms that I just said here. For the self-gravity term, we can again measure it from the cloud internal properties. For the external gravity term, we need to know something about the stellar disk 3D stellar mass distribution. We have 2D distribution from our observations, and we convert that into 3D by an adopted stellar disk scale height. And then finally, for this ambient pressure term, we do not have a very direct estimate of that pressure, but what we can do is that we can assume that the atomic gas is itself in hydrostatic equilibrium, and then we can measure, we can infer the pressure near the midplane by based on the gravity that it feels from all the other components. Now, combine all this together, what we want is to compare this p-term with PDE. And this is what I'm doing in this plot. So on the y-axis, what I'm showing you are the measured turbulent pressure inside molecular clouds. On the x-axis are the expected pressure from dynamical equilibrium, that PDE term, which again constitutes of the three components. Each dot here now represents the cloud population in the KPC size region. And if you look at the distribution of all the dots, they follow quite well this identity line in black. So this is telling us that once you average over a molecular cloud population, this dynamical equilibrium hypothesis can explain the observed property of molecular clouds relatively well. But I just want to note here that both quantities here, again, are population average. So this is not definitely not saying that every single molecular cloud are in equilibrium and therefore long-lived. So this is just saying this is an expected behavior once you average over the cloud population. Now, there are a lot of terms going into the x-axis, as I just showed you. And it is interesting to ask which term is actually doing most of the work. So we can show that by plotting the same x-axis, but showing here the relative contribution from the self-gravity term on the y-axis. there's a trend going through most of the data points. And if you look at the trend at the high pressure end, you have most of the dots above 50%. What this means is that self-gravity of molecular clouds are dominating in this region. But once you go below, at very low pressure inside molecular clouds, you can see that self-gravity ceases to dominate. And instead, the combination of external gravity and ambient pressure start to dominate the total pressure budget. So what this tells us, if we go back to this plot, is that for molecular clouds at high pressure, their internal turbulent pressure is mostly balancing self-gravity. And those molecular clouds are not far from self-gravitating. But for clouds with low pressure, the internal pressure is mostly doing work against external gravity and ambient pressure. So what this means is that these molecular clouds are no longer decoupled from the ambient ISM, and they largely participate in the large-scale dynamics and do things together with the bulk ISM. And they might get destroyed by the large-scale dynamics in a relatively short timescale. Now, returning to the key questions here, the result I just showed has already addressed the first one. So what about the second one? To figure out whether feedback is capable of regulating star formation in galaxies, one way we can do this is that we can measure ISM pressure and star formation rate surface density, and then we can back out this eta FB term. We also have numerical simulations, a lot of numerical simulations that give us a ballpark of what value this quantity can be. And then
Jay, can I interrupt for a second, Jay?
Yeah,
this is
totally.
Norton. Yeah, I want to go back to the question about dynamical equilibrium, and particularly the case of feedback. In the Milky Way, most of the stars are forming inside the molecular ring at around 5 kiloparsecs or thereabouts. And inside of about 7 kiloparsecs, the gas is totally dominated, in fact, by the molecular gas, not the atomic gas. It's like 90% of the mass.
Yeah.
And so there, the external pressure from the gas is obviously negligible because assuming they're in equilibrium, even if you just calculate the atomic gas is basically transonic, so you know its turbulent velocity and its sound speed. So the pressure there is actually lower than the clouds. And that's where all the stars form. And I'm wondering, you have the H1 maps, so you can do the same calculation in yours. And I would guess that in the inner parts, inside of 5 or whatever, 7 kiloparsecs, that most of these galaxies are probably also going to be dominated by the molecular gas. And then at larger radii, it'll be the reverse, because that's what happens in the Milky Way. And then I'm guessing there's still going to be a hydrostatic equilibrium. But have you divided up your sample that way and looked at what's going on? Because in the outer disk, there's not much star formation, but then the pressures are lower, so you don't need that much feedback. So have you tried to do that division at all?
Yeah, thank you. That's a very good question. So I don't have a slide to show you, but in the paper, we didn't actually divide the sample by the ratio of the molecular and atomic gas phase. But one thing we did is that we divide the sample by the total dynamical equilibrium pressure we expect in the galaxy disk. And there's a lot of literature that argues that these two quantities correlate very strongly with each other. So I guess in some sense, that division is effectively dividing the sample, binning the sample by the molecular to atomic gas ratio. And when we bin the sample in that way, we don't see any strong trend in terms of whether self-gravity is dominating or whether the external gravity is dominating. So the trend is just flat. So basically this plot. So if we switch the x-axis into something like the molecular to atomic gas ratio, we will see a flat trend. So I think it means that there's just a lot of scatter from region to region, and it's not a very systematic shift when you go from molecular dominated region to atomic dominated region.
Right.
I don't know.
So that's interesting, and it's not exactly clear why. I mean, in the simulations, we tend to see the same thing, which I certainly don't understand.
Right.
I think the story that the clouds are self-gravitating has been oversold, I guess, is my conclusion. But okay, good. Thanks.
Mm-hmm. Yeah. yeah, and since we stopped, do anyone have any other questions?
Any questions in the room? No. I think we're good here, Jiayi. So
awesome. Okay, so let's pick up from where we were just left. So I just mentioned that we now shift to talk about the second question, which is about feedback. And what we want to do is we can back out eta FB from ISM pressure and star formation rate surface density, and we can compare to our expectation from numerical simulations. So ISM pressure, we already have them measured in the previous parts. And as I just mentioned to you, the star formation rate surface density, we can get them from the combined UV and mid-infrared data. But those measurements are on KPC scales. So there's a mismatch between the ISM pressure and the measured local star formation rate surface density. But we can still plot them against each other and look at what is the implied feedback momentum yield. So now this is what I'm doing here. Y-axis, pressure in molecular clouds measured, and x-axis, star formation rate surface density measured on KPC scales. The ratio between those two is just the eta FB term, and this is typically expressed in units of kilometers per second, as I just said. And just to remind you, this means the momentum injection per unit stellar mass formed. And then we have a lot of results from numerical simulations that tells us what this eta FB term should look like, for example, for supernova feedback. And the expected range is somewhere around 3 × 10⁻³ kilometers per second. And it can go up and down by a factor of few, depending on the local gas geometry and also the clustering of supernovae, etc. So if we put this red box here, which gives you the expected range, you can see that a lot of the dots are above this range. In other words, the pressure in the molecular cloud seems to be higher compared to what supernova feedback can provide based on the local star formation rate surface density. However, I just told you that those two quantities are measured on different scales. The star formation rate surface density are measured on KPC scale. And we know that star formation correlates with the cold gas and they cluster on smaller scales. So it is very likely that our KPC scale estimates underestimate the actual relevant star formation rate surface density for the pressure that I'm showing here. So if we actually take into account the clustering of the molecular gas, which we can see in the CO observations, and we assume that star formation cluster in the same way, we can try to address for this mismatch. And that means that we should move this box up by a factor of about 3, because that's how the molecular gas are clustered in those regions. And once we do that, you can see that a lot of the dots now go inside this box, which means that now the pressure seems to be consistent with expectation from supernova feedback once we account for that clustering of gas and star formation. But there are still a lot of dots above this box. And if you look at it closely, a lot of them are shown in diamond shapes. And those are the regions where we are measuring things inside the bulge of a galaxy or along the bar of a galaxy. Of course, we cannot totally rule out that it might be small-scale gas substructure or supernova clustering, but I think in those regions, it's more likely that other source of turbulence could also be at play. For example, it could be when you have a bar driving gas inward into the galaxy center, you have a lot of released energy from the gravitational potential, and that could also feed the turbulence. So that's the picture here. So
just on that part, can I just act again? Again, you should have the data to check this, right? In those bars regions, you can check to see if the clouds are bound or not, right? You know their velocities, you know their masses and roughly the sizes. You don't really know the scale height because you're looking at them vertically, but you can just assume it's comparable to their size on the sky. So do they have Vero parameters that show that they're bound or that they're not bound?
They're not bound.
Yeah, exactly.
This is something we already know. Yes.
Yeah, exactly. Yeah. So in that sense, it's not a surprise.
Right. Yeah.
What's surprising is that people will tell you that you got to have bound clouds to make stars, and that's obviously incorrect.
Yep. Yeah, we definitely know that the star formation efficiency of clouds drop sharply when the Vero parameter goes up.
Yeah, but it's not 0.
Right. Yeah. Well,
yeah,
some part
you're
of
seeing
the
star formation density in these. That's what you're plotting here, right?
Yes.
Yeah. So it's gone down, but it's not gone down hugely, which I think which actually, was not what people would have told you a few years ago. Right? There are these, Padawan and Northern did these simulations and showed that if you increase alpha, the virial parameter, you get an exponential cutoff. And I'm not sure that that's correct, actually.
Right. Yeah. Well, I think, yeah, I think I agree. Even though we have a highly unbound cloud globally, the small part of them can also collapse inside them and try to.
Exactly. I think that's exactly right. Yeah.
Yeah. Very good point.
So this is probably very naive, right? But is that because what causes the collapse on the smaller scales in the clouds then in those inner regions? I'm just kind of a bit lost there, but.
The initial collapse is not due to gravity, I would say. This is me speculating, not Jiayi. He doesn't have to endorse this. You have to have a converging flow. That's how you make stars. You got to pile up gas. You just need a converging flow, but you don't need gravity to make a converging flow.
Right.
Jiayi's already pointed out these are very turbulent regions, and turbulence will produce converging flows that are not initially self-gravitating.
Right. Okay. I see. Yeah. So it's just turbulence because of the potential at the center is unusual, right? Yeah.
It's not really the potential that's causing the turbulence necessarily. I mean, that's where the energy comes from, is from gas accreting in towards the center of the galaxy. But you stir turbulence on the scale height of the disk, and then you get shocks in smaller regions because of that turbulence. So it's not really the local gravity or the local potential. It doesn't have anything to do with this, which is why alpha, the virial parameter, is so high in these things.
I see. Right. Cool. Okay. Thank you. Thanks for clearing that for me.
Yeah, that's more like the classic picture of you have a log normal density distribution created by the turbulence, and you always have a tail that are extending to long high density, and then when you have high enough density, self-gravity start to kick in, and then you have a power law, and therefore stars. Yeah. Awesome. So if there are no other questions from the audience, I can quickly summarize what I've just talked about in the first half of my talk. So basically, when we look at nearby star-forming galaxy disks, and when we average over a local co-spatial population of molecular clouds, we see that the average property seems to match the expectation from dynamical equilibrium. And we see that high pressure clouds are more close to Twiddle self-gravitating, although there's a factor of a few uncertainty there. And low pressure clouds are more bound by external gravity and ambient pressure. We also look at the momentum injection rate per stellar mass, the eta FB term, and we find that the observationally estimated value is in the ballpark of supernova feedback efficiency as expected from numerical simulations, as long as we consider the clumping of gas and star formation. And this seems to imply that feedback are capable of regulating star formation and keeping it at the observed level, at least in the outer disk part of the galaxies. So now let's move on to the second part of my talk, which concerns about the unobserved third dimension that Norm just mentioned. So this is the depth. So whenever we look at a face-on nearby galaxy, with a picture like this, it is also interesting to ask how thick is the molecular gas along the line of sight direction. So how thick is this thing that we're looking at? And another way to say this is that how large is the vertical scale height of the molecular gas disk in these galaxies? And this is a very important quantity because, first of all, this in combination with the surface density give you the volume density, and that is actually what star formation cares. And in fact, the original Schmidt law was written in volume density terms instead of surface density terms. But also, this vertical scale height is important because, just as Norm mentioned, this determines the outer turbulence driving scale for all of the turbulence in the ISM, and this is also commonly claimed to be the transition point in the turbulence power spectrum from the 3D to 2D. So this is something that's so this scale height we can. If the galaxies were edge-on, we can just measure it directly. But for the face-on galaxies, we'll probably need to infer it indirectly from some other means. But the very classic way of doing this calculation is just to, again, assume plane parallel smooth isothermal disk. And then we will be able to try to back out this vertical scale height by calculating calculated from the gravitational field and the velocity dispersion, the vertical velocity dispersion of the gas bouncing up and down in the galaxy disk. So now I'm doing a very rough order of magnitude calculation. There's a lot of twiddles here. So again, we have the weight of the gas near the midplane. Weight of the gas balances the pressure of the gas near the midplane. Sigma gas, we can already directly observe in galaxies. This little g, we can approximate by gravitational constant times the total volume density of all the mass near the midplane, including the gas and stars, and times the scale height of the gas disk, because that determines how much material are contained in this layer. And then for the pressure of the gas, it's basically surface density divided by scale height, which could be volume density times velocity dispersion. And then if we rearrange these terms, we have the scale height squared is twiddle velocity dispersion squared divided by g rho tot. So this makes sense. If you have a gas disk and you have increased velocity dispersion, the disk will get puffier. But if you had more material adding into this layer, the disk will shrink. So this all makes sense. But one thing that, again, that comes up is we know the ISM is not smooth or isothermal. We know that a lot of the gas mass are contained in molecular clouds. And this means that both this rho tot and sigma gas varies from place to place. And it's not directly possible to use what we measure from, for example, KPC scale observations to just get those quantities over a large aperture and then say, okay, everything is smooth and we get a scale height. There are ways to get around this. One possible way to get around this is to treat individual molecular clouds as individual bullets bouncing up and down. Now, in this picture, we are treating molecular clouds as self-gravitating or self-regulating entities, which is sort of fair game, especially for the massive high pressure ones, because I just show you that in those regions, they are self-gravity dominated, and you do not want the local enhanced self-gravity to screw up the calculations. So in that case, we can sort of use the same formula, but with one caveat. We need to differentiate between the velocity dispersion within molecular clouds, which I call intra-cloud, and the velocity dispersion from cloud to cloud, which I termed as intercloud. So we need to separate those two terms because the dispersion inside molecular clouds, it actually responds mostly to the self-gravity, the local enhanced self-gravity of clouds, and it more or less determines the cloud size, but it does not necessarily link to the total disk thickness. It is actually this cloud to cloud or intercloud term that determine the total thickness of the cloud disk. So this is something that we cannot do previously with low resolution observations because we were not able to resolve individual molecular clouds. But now with the FANGS CO data, we can finally do this and we can test this idea. So this seems like a good idea, but we want to know whether it really works. And it is not easy to answer this question in observations because we don't have other independent means of knowing the scale height in the face-on galaxy. So we tend to simulations for help. We figured that this is a good idea because we know the ground truth, the scale height of all the gas inside the simulations. And actually this kind of calculation, it does not put very stringent require on the simulations. You don't need to have like perfect chemistry and radiative transfer to get all the CO emission right. You just need to have reasonable dense gas with clumpy structures, and then you let gravity and kinematics play out. So this is why I collaborated with Sarah Jefferson, who is now a postdoc at Harvard CFA. So she has a high resolution galaxy scale REPL simulation. The simulation has a mass resolution of about 900 solar mass. So we are very hopeful that the simulations are actually at least resolving individual molecular clouds. The simulation has reasonable star formation and feedback prescriptions that will ensure a realistic clumpy and cold ISM. And the simulation includes simplified on-the-fly chemical network and then post-processing to get the CO emission from those simulations. And then we try to do things in observer's way. We try to calculate an estimated scale height from the intercloud velocity dispersion that we measure from the synthetic CO observations, and then by assuming hydrostatic equilibrium. And then we compare that estimated scale height to the true scale height that we can directly extract from the simulations. Now, so now the plot on the left-hand side is basically the radial profile of the measured velocity dispersion in the simulations. This top line gives you the total molecular gas velocity dispersion, which is basically the combination of the intercloud velocity dispersion plus the intracloud velocity dispersion. So this is something you will get if you just use a kiloparsec scale field observation of a phase on nearby galaxy, because you cannot distinguish those two terms. The blue curve bottom down here is the cloud-to-cloud or intercloud velocity dispersion that we measured at high resolution. Of course, this is lower than that total term because this also includes the dispersion within clouds. Now, in the right-hand side, you have the scale heights estimated from those two terms as a function of radius. Again, the blue and the orange corresponds to those two different estimates, and the black thick line gives you the true vertical scale height we directly measure from simulations. And you can see that estimates based on the cloud-to-cloud or intercloud velocity dispersion match the true scale height, but those based on the sigma-tote overestimates the scale height. So this is reassuring. It tells us that actually our measurement seems to work. So it seems like piecing out between the intra and intra term actually gives a more realistic estimate of the scale height. We also do a sanity check by comparing the simulation results to a bunch of observational estimates in the literature. Now, the simulation is a Milky Way-like galaxy, so we also picked Milky Way-like galaxies, real Milky Way-like galaxies, and observational estimates from them. So now there are a bunch of scale height measurements averaged over the entire galaxy. And this bar on the left-hand side is our estimate based on the intercloud dispersion, which we see matches the ground truth in simulation relatively well. It seems like this estimate also matches direct measurements in hadron galaxies in observations. So if you compare them to the other estimates, so these four are showing you hydrostatic calculations in phase on galaxies based on KPC scale data, so previous version of the data. And this bar gives you our estimate based on the total velocity dispersion, which is what you will get in observation from KPC observations. You can see that all those terms seems to be systematically higher than these observations that we truly trust. So this is telling you that going down to individual molecular cloud scale and differentiating those two terms is crucial for giving you a more realistic estimate of the scale height. So now that we know this method does work, so let's apply it to some real observational data. So these are plots that I just made hot off the press. They are preliminary, but I think they are already illuminating in some sense. So the left-hand side here, so this is measurement in the nearby galaxy NGC 6 to 8. The typical parameter like stellar mass, radial scale length, and star formation rate are sort of close to Milky Way level. And the inclination is very low. So this means that we don't need to worry too much about the in-plane motion screwing up our measurement. The left-hand side plot here shows you the radial profiles of the different velocity dispersions. The thick lines, the solid lines tells you the intercloud or cloud-to-cloud velocity dispersion. The dashed line tells you the intracloud. So again, you can see that even in observations, the velocity dispersion within molecular clouds are larger compared to those between clouds. So it is really important to get rid of this term and get more realistic estimates. And also we test this measurement across a set of different observational resolution just to see if our data resolution will screw up our measurements. It seems like there is some systematic trend. So if you go from low resolution to high resolution, meaning smaller beam size, typically you tend to break things apart into smaller things. And then you will attribute what you previously thought as intracloud into intercloud. And therefore you have a higher intercloud velocity dispersion. So this trend makes sense. But this is not a wide range. It's only a very small factor, like 0.2 DEX at most. So this gives us some confidence that our measurements are not strongly dependent on the spatial scale that our data are at. And then on the right-hand side, we're comparing the inverse scale height from the intercloud term. and compare that also to the measurements in the Milky Way. So we can see that actually those two are sort of comparable in the ballpark of each other. So it also tells us that seems like our measurements are working. Here's another example. This is a slightly lower mass galaxy. And also the thing about this is that the inclination is relatively higher. So there could be more contribution from the in-plane motion, and we need to be more careful about removing those to get the vertical, the actual vertical component. But you can see sort of the same thing. The intra-cloud term is slightly higher than the inter-cloud, and the inferred scale height seems to match the Milky Way relatively okay. So these are very preliminary results, but we plan to widely apply this to all galaxies with reasonably low inclination and further look at dependence on the galaxy global properties such as global stellar mass, radial scale length, etc. So I'll briefly summarize the second part of my talk here. I hope I've persuaded you that it is possible to reliably estimate the vertical thickness of the molecular gas disk in phase-on galaxies, even though we know that molecular gas is pretty clumpy and far from parallel isothermal. Results from numerical simulations, from several simulations, seems to say that the scale height is mostly determined by the cloud-to-cloud velocity dispersion. And if you mix it with the intra-cloud term, you will lead to an overestimation of the scale height. And finally, we plan to apply this method to high-resolution thanks data to determine the full 3D molecular gas distribution in those phase-on nearby galaxies. So I will end my talk here, and happy to answer any questions you have.
Jiayi, we'll give you a real-life round of applause in the room.
Thank you.
Also a virtual one. That was great. Okay, any questions for Jiayi? Yeah. Scott has a question.
I actually have, first.
I'm sorry, I cannot hear you.
Is that? Sorry, Scott. Can you hear?
It goes in and out.
Okay, maybe.
Okay, I have two questions. You probably said this, but it's not clear to me how you measure the difference between the intra-cloud and the cloud-to-cloud velocity dispersion in galaxies. And the second question is, all of the galaxies that you showed, the intra-cloud dispersion and the inter-cloud dispersion seem to be about the same within a factor of 2. And is there any obvious physical reason why that should be true?
Okay. Okay. So the first question is how we measure those two terms in observations. So the way we do this is that since we have cloud scale CO data, I don't know if I have a picture. Well, I do have a picture. So in this plot, all the blue things are the CO observations. So these observations are reaching down to individual molecular cloud scales, which means that we can identify cloud-like objects. So we can draw contours around these things, and we try to separate them in the 3D cube, actually, not in the 2D maps. And once we have separated them into individual objects, what we just do is that for the intra-cloud term, we just measure the CO line width for each cloud, and we do, again, the mass-weighted average across all the clouds in each KPC scale chunk. And then for the inter-cloud, we need to be more careful. So we first need to remove any residual contribution from the in-plane motion, even though most of the galaxies are relatively face-on. That means that we need to use a prior velocity field that tells us what's the in-plane motion. And for that, we use like a smooth version of the CO observations, which give us like the large scale motion. And then we subtract that off, and that left us with the small scale velocity dispersion. And we assume that it is the cloud-to-cloud term that is dominating this residual. So that's how we get the inter and intra. And then to answer your second question, whether there's any physical reason those two things are always close to each other by a factor of few, I personally don't know. I think there are physical reasons they should add up to the same value total. I mean, of course, it varies from place to place, but if you look at different galaxy resolutions, then the two curve with the same color should add up to the same total, because that's what you will measure from KPC scale. But the division between those two, it is not clear to me if there's a physical reason why one should be comparable to the other or not much larger than the other.
I can speculate if you want to hear, Scott.
Yeah, please.
It's telling you that the clouds, the ones that are bound, don't live long. Because if they live long in terms of their eddy turnover times, the turbulence would dissipate, they'd shrink, and their velocities would go up. And that upper line would move away, the upper dashed line in the plot there would move away from the lower solid line. Because as the clouds contract, their velocities go up. So the fact that they're close tells you that the clouds, once they start becoming gravitationally bound, they quickly get disrupted. Otherwise, that difference would be a lot farther apart.
Okay.
Scott has a comment.
I think that, yeah, that sounds reasonable.
Okay. Since Norm volunteered an answer, let me ask a question about planet dynamics, which is that in formation of planets, you find that the Safronov number, which is the ratio of the escape speed to the velocity dispersion, is typically near unity. And in that language, what you're seeing here is that the Safronov number is near unity. And that basically says that the relaxation time from gravitational scattering is comparable to the collision time. So is that an alternative hypothesis as to why the two dispersions are similar?
Well, as I say, that explains it initially. I think that's correct. But unlike planets, there's no reason why this gas can't continue to increase in density, right? Planets are subject to degeneracy pressure. So they can't get, more compact, and therefore their surface velocities are sort of fixed by their size. That's not true for GMCs. They can continue to collapse, and they do, which is why stars have escape velocities of several hundred kilometers a second, because it's the bits of the cloud that manage to keep condensing. Stars, of course, are held up by either thermal gas pressure from thermal nuclear reactions, which planets don't have to worry about, or when they get small enough, they're held up by degeneracy pressure. But clouds, they can keep shrinking, and their velocity dispersion will keep going up. And so it's not just the same thing as in planet formation. They really have to be disrupted. Otherwise, the velocities would be much higher than you see.
Okay, Antoine, you might have to come up here. I think it's.
Hi, this is Antoine. Thanks for the great talk. I see an interesting parallel between this method to estimate the scale 8 and what we're doing in the neutral ISM. So we do pretty much the same thing, but we see the CNM clouds as well. We measure the inter-velocity dispersion between the CNM clouds. When we do that, we can probe because they are moving and born within the warm neutron medium, the velocity dispersion of the warm disk. So I think we could apply exactly the same thing to the neutral ISM, trying to then match and measure the scale 8 of the CNM layer and the WNM layer in 3D. I'm even wondering if when you measure this inter-velocity dispersion between molecular clouds, what you're measuring is actually you're probing the turbulence in the CNM layer by doing that, because they live inside the CNM layer, in my opinion. Yeah, so that was more a comment than the question. But thanks again.
Yeah, thank you. That's a very interesting comment. I think I would agree with you if the molecular gas disk scale height is the same as the CNM disk scale height. But I just don't know a priori that that's the case. It might well be the case, yeah. But I don't have a given observational proof for that. So, but that's a very interesting thing to see. If you can measure the CNN cloud intercloud velocity dispersion, maybe we can compare measurements in the same galaxy if we have.
So I have a question about that. You're using 21 centimeter, right, on large scales, unfortunately, to measure the. So do you see, like in the CNM in the Milky Way, you can see narrow 21 centimeter and broad 21 centimeter lines in the same direction. So the cold neutral medium has a fairly narrow component, and then there's a broader component which is like a, temperature of several thousand or whatever it is. Do you have enough spectral resolution to see that kind of effect in your extragalactic observations?
So sorry, is that question's for me?
Yes.
Okay.
Because you have 21 centimeter observations of these galaxies, right? I mean, maybe you guys didn't take them, but they're available.
Yes. So for most of the observations we take, the velocity resolution is pretty bad. It's like it can go up to like 10 kilometers per second. So
okay. Yeah.
I don't I don't know.
So you can't do that. Yeah.
Yeah.
Now the cold neutral medium, if you look at the 21 centimeter emission there, you see these narrow lines that are like, less than of order kilometer a second or less. So you need really good resolution. So
yeah.
Carl Hylas does this for a living.
Got it. Yeah, that's pretty cool. I think so I know that we have very high resolution H1 for M33 from Eric Koch. So maybe I think he will be interested in trying this out in his observations. Yeah, but it is not part of things.
Yeah.
Cool. Any more questions online? Just go ahead and speak up. Okay, I've got another very naive question, and I guess it's kind of related to what Scott asked about the plot with the intra-cloud versus the cloud-to-cloud dispersions. You kind of got these like wiggles. Are they? Is that like the spiral arms in the galaxy that you're seeing? There's like the wiggling that's going on, and you don't see it in the cloud-to-cloud. Oh, sorry, you don't see it in the intra-cloud, but you see it in the cloud-to-cloud. And does that tell you something about the star formation being sort of driven by spiral structure and things, or is that being just very stupid?
Yeah, well, that's a very good point. So the wiggle, I should definitely check back and see whether those wiggles actually correspond to the radial beam that you have a large part of a spiral arm with molecular gas things. But I think my observer's mind will first worry about our our treatment of separating clouds get screwed up in the dense spiral arms because all of those clouds are connected to each other and it's hard to distinguish them apart. So maybe like we have first observational artifacts kick in. And if I vary that that's not the case, maybe I would be more comfortable moving to a physical explanation then.
Yeah. So I guess it'd be interesting to like mask out the spiral, because you can see the spirals in image, right? Just like mask them out and see if you kind of, I guess, yeah, I hadn't really thought about the fact that you've averaged as a muesli, right? So they should get like,
yes,
any effect should get kind of blurred out. But
yes, yeah, that's a good point. So we do have like environmental masks, which tells us where the spiral arms are. So we have those data products available. We can definitely mask out the spiral arms, but that means we are throwing away 70 to 80% of our measurements. Now we can focus on the remainder, like the spotted clouds in the interarm region, and see if we can still get a reliable thing. But yeah, but that's a good idea. Yeah.
It was just interesting to me that the difference between the two curves changes like in those wiggles, and I wonder whether there's a physical reason for that. But
yeah, totally fair. I should write this down.
Cool. Okay. If there's no more questions online, no more in the room, I don't think, unless there's any final comments from Scott or Antoine. Okay, great. I'll give you another round of applause. Thank you very much, Jiayi. It was great.